Hello, everyone. Welcome to the Audio Precision webinar. Today we'll be discussing MEMS microphone test with the new APx517B. Daniel Knighten will be leading the conversation, and he'll be providing demonstrations in APX 500 software as well. My name is Paige, and as the producer of the event, I would like to go over a couple housekeeping items before we get started. So first, please note that this session is being recorded. And secondly, we welcome questions during the webinar. So if you have a question for Daniel, you can submit it via the chat function in Microsoft Teams. You should see that in the corner of your screen. We'll also pause to answer questions at the end of the event as well. Dan has a lot to share with you today, so without further ado, Dan, I turn it over to you.
All right, thank you, Paige, and good morning, good afternoon, or whatever time zone you may be. Welcome. So in this hour, I'm just going to go over really the practical side of measuring MEMS microphone with a PDM output. We do kind of generically assume that a MEMS microphone has a PDM output, and that's what we'll be demonstrating today. But there are MEMS microphones with analog outputs and MEMS microphones with I2S outputs, and those would have some slightly different physical configurations. But in general, actually most of what I'll demonstrate today will apply to any situation in which you want to find, I'll say the basic parameters, the frequency response, phase response, and sensitivity of a microphone. I'll talk about sort of prerequisites for that task, physical prerequisites, peripheral devices. And in this case specifically, we've announced the APx517 acoustic audio analyzer, which is particularly optimized for this task. The meat of the presentation will be spent really working with the software, and if you have any practical questions from your own experience that you'd like answered, this would be a good place to address them. And really a lot of it is spent in the setup of our test configuration. As you'll see, once we have everything set up, making measurements is pretty straightforward. And I'll show three specific measurement techniques using a step frequency sweep, an acoustic response with our log chirp, and then our transfer function measurements. And I'll talk about why we might use each particular measurement, and then we'll try and reserve some time for question and answer towards the end. And as Paige mentioned, feel free to submit any questions you have as we go in the chat window. We'll be monitoring that, and we'll try and address them as we go, though we might pause at certain areas. Okay, so first of all, why an APx517? So those of you already familiar with Audio Precision's product lines may know we have, a wide variety of different configurations for audio analyzers, from 2 channels to 16 channels, and with various degrees of analog performance and various options for analog connectivity. Pretty much any of our audio analyzers could be used for this task. The advantage of the APx517 is it really has all the specific inputs and outputs that will be useful for this task and will minimize the need for external peripherals. So specific to the task of measuring a microphone, the first thing we have is on the left of the front panel that you might be able to see is a power amplifier. And we're going to use that today, not because we're going to measure a speaker, we're going to use it today to drive what we would call a source speaker, the device that's going to provide the acoustic stimulus signal for our measurement microphone. On the input side, we'll be taking advantage of 2 things. The first is we have analog inputs that directly support measurement microphones. So in this case, we're going to be using a measurement microphone that requires CCP or IEPE or ICP, DC constant current source to power the microphone. And that means we don't need an external microphone power supply or preamp. And then though this picture does display a Bluetooth module installed in the 517, the 517 we're going to demonstrate this morning actually has a PDM16 interface module installed in it, and that's connected to a development board with 16 PDM microphones. So really the key here is with the 517, we have pretty much as simple a physical configuration for this test as we can, since all of the peripheral devices, which is a source speaker, a measurement microphone, and then the actual PDM microphones under test will just be connected directly to the front panel. I won't have an external power amplifier. I won't have an external microphone power supply or preamp. All of it will be directly integrated. And frankly, thanks to that integration, this comes in at a considerably more economical price point than some of our other solutions. Now, Audio Precision does actually offer 2 digital interface modules that support PDM or pulse density modulation. We have one module called just PDM, and we have a newer module called PDM16. And here you can see a little bit of a comparison of the features between the two. Very broadly speaking, the difference is a little stark. If you need to test more than 2 PDM microphones simultaneously, PDM16 is the obvious choice. The other difference between PDM and PDM16 is PDM16 has a remote interface pod. I'll have a picture of that in a moment. But that remote pod essentially moves the front panel of the analyzer to your test environment. And that can be on up to a 10-meter or 30-plus foot cable. And so physically, that means you don't have to have the entire analyzer in the test chamber. You can just have a very small pod. And also from a signal integrity point of view, most PDM microphones cannot directly drive a very long cable. So it's always been a little inconvenient to use the PDM module when testing a microphone that's far from the amplifier. We do have a PDM line driver accessory that's a little bit different than the PDM16's remote pod. The PDM line driver sort of boosts the signal and makes up for the ability to drive a capacitive load that you see in some PDM microphones. Unfortunately, you do still see ringing and other artifacts from impedance mismatches and other long cable issues when you use a PDM line driver that don't occur with the PDM16's remote pod. I do want to address a question, which is asks, power amplifier is mono. Can it play both outputs at the same time? The answer to that is no. On the 517, there is an A-B switch. There are 2 connectors for the power amplifier on the output. That's designed to let the 517 share 2 physical test jigs, but the actual power amplifier signal comes out of one or the other. Thank you for that question. Okay, so then the next question is a much more applied question and a little bit independent of the APX itself, but that's what's our test environment for measuring these microphones going to be? And this is a very practical question. Ideally, we all have access to an anechoic room. A room without any acoustic reflections. I think the practical reality is most of us do not have access to an anechoic room. Now, there are some benefits to measuring microphones compared to, say, speakers that let us be a little bit more flexible. One common solution is to use a test box, which is essentially a very small anechoic chamber. The one that's pictured there is sort of, I'll say, good down to about 200 hertz, which actually, particularly if we're testing microphones for voice applications, can be perfectly acceptable. Now, what I'm actually going to do today for our demonstration is I have the microphone array, which is pictured there. It's a little dev board with actually just 16 microphones in a line. I actually have that on a tabletop surface. If you'll pardon my abuse of the term, I'd call that a half space. And what I'll show to you is that this can actually be quite a good solution for certain measurements. I wouldn't use this to measure directivity, but in our particular situation, we will be able to get phase data for the microphones, and we will actually be able to check their sensitivity. And we've got another question. Is it possible to read sensitivity from analog and digital microphone at the same time? Yes, and I'll show you that exact item in just a moment. Okay, and then the next practical consideration is going to be, what do we use as a source speaker? And this is this is a very rich topic. I'll go over it very briefly. If you are testing microphones, particularly for voice applications, so a microphone that's going to go into perhaps a mobile phone or a smart speaker, and you know, the bandwidth is 200 or 400 hertz to 8 or 16 kilohertz, and really the goal of the microphone is to pick up speech signals, a further property of the device may be a requirement to test it against voice telecommunication standards. And the reference for that is a mouse simulator. Pictured here is the mouse simulator that we provide, a GRASS 44AA or AB model. The, I'll say, downside of a mouse simulator is a mouse simulator is not actually meant to be, I'll say, a great speaker. It's meant to simulate the acoustic properties of a human speaker. And that has influence on the output level it can achieve. That influences the bandwidth over which it can operate and its frequency response, and a lot of other properties. So that let's say that you're trying to make broadband measurements of a speaker in a free space at some distance. A simulator may not be the optimal choice for that situation. When we're just looking for a speaker to generate test signals over a broad range, now the considerations are really bandwidth over what frequency range we want to be able to generate those signals, the signal levels we need to generate, and then, frankly, what our budget is. And I'll talk a little bit about the practical side of using a source speaker when we talk about equalizing the source speaker. But I'll say that generically, at that point, what we're looking for is a speaker that can generate test signals over the frequency range of interest and at the acoustic output levels that we're interested in testing at. And that might drive you, no pun intended, to a pretty expensive source speaker, perhaps a professional studio monitor like the one pictured. But actually in the application today, I have the speaker fairly close, just about maybe 10 centimeters from the device under test. I'm using this over sort of the speech band So I want to go from a couple hundred hertz to 10 or maybe even 20 kilohertz. And I don't need to generate exceptionally high sound pressure levels. So in this case, what I'll actually show today is using essentially an off-the-shelf consumer speaker that we're going to calibrate and equalize. Okay, I'll talk a little bit about why we'll use a reference measurement microphone when we're demonstrating the application. But for the moment, let's just assume that we're going to use some type of microphone that will be our reference. And there's quite a bit of flexibility here. And again, it has to do mostly with the frequency range of interest. And one thing I'll touch upon is that it's pretty straightforward to get a measurement microphone that is going to have a flat magnitude response, so a flat frequency response over probably whatever frequency range you're going to be practically interested in measuring in another microphone. But particularly if we're looking at phase response, and that's often a key question when we're measuring microphone arrays, MEMS microphone arrays for, say, smart speaker applications. We're really very interested in the phase response of our individual speaker microphones under test. Then there's a pretty big difference. A standard half-inch microphone, the phase response is only flat up to about 1 kilohertz, and then it starts rolling off. And that's, what we're observing is actually the resonance of the microphone diaphragm itself. So practically speaking, the smaller the microphone diaphragm, the higher the frequency to which the phase response is going to be flat. And so actually for today's exercise, I'm using a 1/4-inch pressure field microphone. And that is because the 1/4-inch pressure field microphone, the phase is down just 30 degrees at 20 kilohertz. It's much flatter up to a much higher frequency. Now, the other benefit of just using a small microphone is that I'm going to have the measurement reference lined up physically with one of the microphones, the reference position in the array of microphones that I'm testing. And the microphone, the reference microphone, is not acoustically transparent. It is sitting in the sound field. And so there's simply a benefit. The smaller the microphone is, the less disturbance to the sound field it will make. Okay, so then this is actually pretty much exactly what our setup looks like today. I've got a source speaker connected to the power amplifier A connector, and we'll use that to generate a test signal. I've got a 1/4-inch microphone that's sitting just off from the microphone array under test, and that's also connected to my 517 front panel. And then for my digital I/O module in the 517, I have a PDM16 module, and that has a relatively long tether going to the pod, and then the pod has just a ribbon cable that interfaces to the eval board. And just a couple more questions. So one question is PDM microphones have gotten quite tiny, and they are indeed. The PDM microphones are actually often smaller than even a 1/4-inch mic diaphragm. And positioning the reference mic at the exact position raises some challenges, and it makes accuracy challenging. And how do we cope with that? And number one, I want to observe that is exactly true. The MEMS microphones have gotten extremely small, which is frankly a benefit for them. And so how do we position the reference microphone both at exactly the right spot and so as not to interfere with the acoustic sound field around the microphones you're trying to measure? So the answer, if you will, is really a little bit more complicated answer, but it really comes down to what is the highest frequency you want to accurately measure. And to put that into perspective, at 20 hertz, the wavelength of sound is extremely long. It's, I believe it's around 10 meters or so. So at that frequency, if we were measuring 20 hertz, these microphones could be, especially if we were in a free field, could be meters from each other. And it wouldn't make a difference because the wavelength is so long. If we're measuring at 20 kilohertz, the wavelength has gotten so short that minute differences in position, millimeter differences in position, will make a difference in the measured sound field. So there's frankly no way around that. If you are measuring to high frequencies, and the higher the frequency, then the more mechanically precise the positioning of all the items will become. And in fact, the more challenging things will get, because in today's demonstration, I have the reference microphone very close to, not within a few millimeters of the lead microphone under test. If I was measuring, if I really cared very precisely about the response all the way to 20 kilohertz, that would present a challenge, because to get the microphone close enough, it would then be interfering with the sound field. For voice applications, we're generally testing up to about 10 kilohertz. And so that gives us just a little bit more physical flexibility in the positioning of everything. But the point is completely acknowledged, and my answer is it depends on the highest frequency that you're interested in accurately measuring. That will determine how mechanically accurate the positioning of all the test articles needs to be. And then I've got another question about 1/8-inch microphones. 1/8-inch measurement microphones do exist. They're a little bit esoteric. Relatively rare and expensive, but they do exist. And exactly in the situation for where you need to measure to high frequencies, that's really where they become quite useful. Now, 1/8-inch microphones do have the property that their sensitivity is even lower. They can have sensitivity even below a millivolt per Pascal. So that introduces some other challenges, but they definitely do exist. And if you need to measure to high frequencies, you may find some utility in all of that. And then just to address a couple other questions. Is there a single clock source for all 16 PDM channels, or are there multiple clock sources? It's a single clock source in the PDM16 that is electrically buffered to drive all the microphones. And another user asked, for a standard PDM module, we usually use PDM line driver. What will the maximum length that can be used with 16 channel modules? The 16-channel module, the maximum length cable we sell is 10 meters. If you need a longer cable, that could probably be custom made. But the nice thing there compared to the line driver is the transmission system from the module to the pod is a low voltage differential signaling protocol that gives us quite a bit of flexibility in the length of that cable. Okay, so now let's go hands-on here and let's look at actually configuring this in the APx software. I'll just start from ground zero here, what it looks like when I've just started the software. And as far as our configuration, I'm here in signal path setup, and I'm just going to go from top to bottom. So on the output side, I am going to use the power amplifier. I'm going to use output A. And for right now, I'll just check the acoustic checkbox because I will calibrate that speaker so I can set my generator level in dBSPL or pascals. On the input side, I'm going to eventually use two inputs, but I'll start out with my first input, which will be for my reference microphone. I'm only having one analog input for one reference microphone. I'm going to use that in acoustic mode. And now going down further, it is on the unbalanced input, and I do need to power that microphone. So I'll select CCP. It's a 4 milliamp microphone. That we do have the 10 milliamp choice for CCP devices. I'll turn the power on to that microphone. And now I need to calibrate it. Now I need to reveal that I'm not, unfortunately, in the office due to the current situation. I'm working remotely. And in the office is all the physical equipment. So I'm doing this remotely. So I'm going to take advantage of the fact that I can select Calibrate from TEDS. And I can read the calibration information directly from the microphone electronically. And I'll go ahead and set the sensitivity from that. Now, I will say that strictly speaking, calibrating from TEDS is a bit of a misnomer. I'm not really calibrating the microphone. I'm reading the previously stored calibration data out of the microphone and using it. So, you know, if I was being very, very thorough, I might separately attach an acoustic calibrator to the microphone to verify that the calibration hasn't changed since the last time I've used it. But this is a microphone I use fairly frequently, so I'm satisfied with the TEDS data. Now, at this point, I could just go, but one additional thing I'll do here is I'll reduce the analyzer bandwidth to 22 kilohertz or 48 kilohertz. And that's just so I'm not collecting and processing data above the frequency range of interest. That's just, I don't have to do that, but it'll make things a little easier for me down the road. So now I'll expand verify connections, and I'll just turn on the signal generator and verify that I get a signal. And I see that in my FFT input monitor, and then also here in this level meter. Now, surprisingly, I'm not actually, even though I haven't calibrated the speaker yet, I'm not too far off. I've set the generator to 80 dBSPL, and I'm getting 81 dBSPL, so that's actually kind of just lucky. I'm now going to go to references, and the first thing that pops up is output references, and I'm going to go to acoustic, and I'm going to calibrate the output level of the the speaker, and this is going to be by reference to the measurement microphone, and this is where, you know, the position of the reference measurement microphone becomes relevant, because later on in this exercise, when I'm setting the generator level, that's going to be the generator level at the reference position. So I'll click on output. I'll calibrate this to 94 dBSPL. And what I'll let the software do is automatically hunt for that level. So I'll say, yep, it's somewhere between a millivolt and 2 volts. I realize that's quite a large range, but it will figure things out. Okay, and there we go. Now we've set the generator so that if I go back to verify connections, and let's say I set this to 80, now I'm getting 80 dBSPL. If I go back to 94, I get 94. I can probably maybe I can go up as high as 100. Now keep in mind that one of the things that we'll be subject to here is the linearity of the speaker. And that's why typically when I calibrate the reference level, I calibrate that to whatever test level I'm going to use, because that's really all we're guaranteeing. I mean, here the speaker is quite good. We calibrated at 94 dBSPL. When I set the generator to 100 dBSPL, we're quite close. We're within 0.1 dB, so this is a pretty well-behaved speaker, but that is by no means guaranteed. So if I'm going to use 94 dBSPL as my test level, I calibrate the speaker to 94 dBSPL. Now what I've just done is to calibrate the amplitude of the speaker at one frequency, at 1 kilohertz. So I'll go ahead now, as I'm going to add a measurement. Let's just add acoustic response. And let's measure the speaker's frequency response, and let's do it at 94 dBSPL. I'll do a slightly longer sweep. Let's do like a 2.5 second sweep. And let's look at the frequency response. So if we look at 1 kilohertz, we do in fact reach our target level of 94 dBSPL. But over the rest of the frequency range, we are seeing the, I'll say, natural frequency response of the speaker. And this is a small little single driver speaker, so the frequency response falls precipitously below 200 hertz, and then it has some irregularities around high frequencies. Now, as I'll demonstrate in a moment, I could potentially use this as is. By having a reference microphone, I could, in some sense, divide out the response of the speaker. But what I'm going to do is equalize my speaker. Now, when I equalize my speaker, I've got to be aware of the fact that I can't equalize, I can't boost the output of the speaker at 20 hertz enough to get to SPL. I can generally equalize the speaker over some reasonable range of output. So let me show you what that looks like. I'll go to my relative frequency response result, and I'll go ahead and export this data. And I want the relative level. I'll take all data points, and I'll say and now I'm going to go to EQ. I'll select relative, and I'll import that. And you can see here I just have the frequency response of the speaker, so I'll invert it. I'll say OK, and let's just compare data. Whoops. So exactly, it says, hey, the value of plus 149 dBSPL is out of range. And that's exactly a little obtuse way of complaining that at some frequencies, the amount of EQ required to get the speaker to be flat is just not achievable. So let me close that window. And now let's look at a tighter frequency range. Let's EQ it, or let's run the sweep from 200 hertz on up. Okay. And so now I'll just uncheck this. So this looks quite noisy, but it's because we're quite zoomed in. Let's go and look at. And now we can see that we're actually able to achieve a quite flat frequency response from this source speaker by calibrating the output level and equalizing its frequency response. Now you can look at it in absolute. You can see we get our nice 94 dBL over quite a broad frequency range. So now that I've captured that equalization, let's take a look at configuring our PDM microphones. So I'm going to click back to go back to signal path setup. And I'm going to go to input number 2. And I'm going to select PDM16. And I'm going to turn the clock outputs on. And I'll turn the PDM, VDD on. And by the way, if you wanted to set some additional functions like the decimation rate, whether we're generating the clock or receiving the clock, the voltage levels, that can all be set in advanced settings, but I'm just going to use the default values, 64, 1/64 decimation. From a 3 megahertz bit clock, that'll give us a 48 kilohertz output sample rate. And now what you'll notice is if I look at the input signal monitor, I've got an updating FFT. This is the signal from the reference microphone, and then these are the 16 signals from the PDM microphones. And then I'll go down here and I'll add a new primary result. Let's just add RMS level, and let's add that to PDM16. And if I go back to verify connections and I turn on my signal generator, early in the conversation, somebody asked, hey, can we check the sensitivity of these microphones, the analog reference microphone and the PDM microphone simultaneously? And the answer is yes. This is a new feature that was added in the software recently, but now I can simultaneously look at 2 inputs. And one thing that's convenient is I can look at the analog reference microphone and I can verify it's receiving 94 dBSPL. And then here is the signal that I'm getting from each of the 16 PDM microphones. You do see some effects here of the fact that my physical setup has the source speaker quite close to the PDM microphones. So we are actually seeing a little bit of effect of the sound pressure is diminishing noticeably between the closest and the furthest microphone. But we can see we're in that range. These PDM microphones, I think their spec is officially minus 26 dBFS at 1 Pascal. And if I wanted to, I could add a new derived result. We have this derived result sensitivity. Our comparison data is going to be PDM16. And I can add and here is the relative sensitivity between the PDM microphones, 2 of them, and the reference microphone, and here it is directly in dBFS per Pascal. Okay, so we now have everything set up and ready to go, and we can make some measurements. So I can do this a few ways. Let's just start out by selecting Add Measurement. And let's start out with a good old-fashioned stepped frequency sweep. Actually, sorry, let me start out with just acoustic response. Okay. So one of the things I just wanted to show here is some of our measurements have a lot of results, and when you add a second input, well, that's going to double all the results. So it's times like this when it can become quite useful to say, well, what results am I really interested in? And I'm going to say, let's go. I want the impulse responses and the energy time curves, the RMS level, relative response. Well, let's go ahead and look at delay and phase and group delay. But I don't care too much about these other results, so I'll leave those unchecked. And I'm going to right-click on this measurement, and I'm going to say delete unchecked results. And that will just clean up all the results I have quite a bit. Okay, so from here, let's make some measurements. So I'm going to select the frequency range, and I'm just going to go from 200 hertz to 20 kilohertz. I'll do this at 94 dBSPL. Let's use our equalization curve that we previously captured. And it's a little bit arbitrary, but I'll just do a 2.5 second sweep. So first result here we're looking at is the impulse response as captured by our analog measurement microphone. Then we have 16 impulse responses, one for each of the PDM MEMS microphones. And then similarly, we have the energy time curve. And here we have the frequency response of the reference microphone, and we equalize the speaker, so it's pretty flat. Here we have the responses of each of the MEMS microphones, so this is the magnitude response. And again, the relative level, so normalized to 0 dB. Again, for the MEMS microphones. Maybe what's a little bit more interesting to look at is the delay. So here you can see how the furthest microphone is, in fact, a little bit farther away than the nearest microphone. We can check out the phase of the reference microphone. And that's kind of what we expect. A linear phase, that's just the delay or the time of flight. And then we can do the same here at our MEMS microphones. I'll come back to this in a moment. But very similar, and again, we can see the linear delay. Now you'll notice that this is so-called input to output phase, so this is the phase relative to the source speaker. And then here's, group delay, which is a little bit noisy, but that's because we're highly zoomed in. That is, I'll say, the most direct result. Now let's look at this a few different ways. Since we have equalized the speaker, so we've got 94 dBSPL across our swept frequencies, to some extent, we can just read the sensitivity right off of one of these graphs. Now, it is biased because there's a microphone that's very close to the speaker and there's a microphone that's relatively far away. So we're seeing some of that effect. But let's just set this aside for a moment and say, well, I'm generating 94 dBSPL, 1 Pascal. So, the sensitivity of mic 1 is, well, just about minus 25 dBSPL per FS. There are additional little things I could do here. So let's go to my RMS level result. I'm going to add a derived result. And again, I'll choose sensitivity. And our comparison data is going to be PDM16. And let's just look at one result, one PDM microphone for right this moment. Let's put this in dBFS per pascals. Okay, so let's just make this graph not quite so crazy. I don't know. So what's interesting about this result is that this is the frequency response of this PDM microphone relative to our reference microphone. So we can also read sensitivity directly from here. And in fact, let's just take another derived result. I'll set that aside, that little warning for a second. But exactly, this is just the sensitivity derived from this graph of the sensitivity or the ratio between our sound pressure level as measured at the reference microphone and the output of the PDM MEMS microphone. The thing that's handy about this is this kind of divides out the speaker response. And let me show you what I mean by that. I'll disable the EQ and let's just run this measurement again. If I look at my frequency response again, now it's got all the wobblies of the speaker itself, and that's coming through. This is as measured by the reference microphone, but we're also seeing it in the MEMS microphone. I'm sorry, over here. But if I take look at the sensitivity result, which is really this result divided by this result, those wobbly wobblies are taken out. And again, I just get the response of the MEMS microphone. Let me make that more apparent by appending the results here. Oh, sorry, let me and we want so you can see that they actually land right on top of each other. And that's actually maybe one of the biggest advantages of using what I will call the simultaneous mic substitution measurement technique of using a reference microphone positioned near the microphone under test, is that one of the things this does is gives you quite a bit more flexibility in the source speaker that you use for your tests, because that speaker doesn't have to have a perfectly flat output. It gets divided out by the reference microphone. Okay, so just a few more minutes left, and so let me show you one more relevant measurement technique, and that's transfer function. Transfer function's a relatively new result we added in APX. We added it in 5.0. And transfer function is particularly useful for this application for two reasons. Number one is it lets us use a non-sinusoidal signal as the test signal. Particularly, we'll be able to use speech. And the second is that it will let us calculate a transfer function between input and output, or any two inputs. So let me show you what I mean here. So on waveform, I'm going to select Browse for File, and these are IEEE real speech signals. So I'll select male mono. The output level, so this is a little complicated. In APX software, output levels are always calibrated for the peak of an equivalent sine wave. That's a little bit long explanation, but the short is this signal has a much higher crest factor than a sine wave, so I need to boost this output actually to get the signal level I expect. We're just a little short on time, so I won't go through the process of finding and setting that. We might do a separate blog post on that, but I'll go ahead and just put this to 114 dB SPL, which is calibrated against a sine wave to get the signal level I want. And then on the transfer function, there's a question of what we're going to calculate the transfer function relative to. So let me do this. I'm going to calculate the transfer function relative to our reference mic. Match has to do, you might think of this as triggering. In this case, we don't need to trigger, so I'll set this to none. And then time alignment. So I actually want to see the phase relative to the reference mic, so I'm also going to set this to none. I'll leave calculation mode alone. I'll make my FFT length 48K so I get 1 Hertz resolution. And this speech signal is 12 seconds long, and it's a non-repeating signal, so I want to do a bunch of averaging. And let's do 50% overlap, and I'll just set this until I get my full 12 seconds of that test signal. And now let's start this. Oh, this is a good warning. So the input range changed on the analog mic. So I need to fix that input range. So I'm going to go into advanced settings, disable auto range, and that's fine for right now. Okay, so my first result here is a straight line because this is the frequency response function of the reference mic compared to itself. Here we have something more interesting. This is the frequency response function of the PDM microphones with respect to the analog reference microphone, all 16. Again, the phase of the reference microphone itself is not interesting, but here is the phase of the PDM microphones compared to the reference microphones, reference microphone. And we do have some garbage up at high frequency, and I'll explain that in just a moment. But let me go here and zoom in a little bit. So here we have the phase of all 16 microphones calculated with respect to our reference microphone. Okay. So now let's talk about coherence. Coherence is a very useful result out of transfer function. It tells us how closely the energy in the response signal matched the energy in the reference signal. And one downside to using speech as a reference is that human speakers do not produce white noise out of their mouth. We produce energy over a pretty defined frequency range. And what you can see here is that the coherence of this test signal is pretty well defined. We have good coherence above, say, 150 hertz, and it gets somewhat noisy, but then really falls off like a brick above 8 kilohertz. And so we need to keep that in mind when we look at all our measurement results. So everything from the frequency response to the phase response, I'll say, is a bit janky when we're outside the range in which our test signal had energy. But this is a quite handy way of doing things, particularly, for example, let's say we're testing a smart speaker where we can't use a sinusoidal signal for the test because there are voice processing algorithms that will ignore sine waves. We can use an actual speech signal as the test vector, still get our frequency response. We can still get sensitivity. In fact, that's one of the, because we're calculating the, since we're calculating the transfer function relative to that reference microphone, we directly get sensitivity here. So here's our frequency response expressed as dBFS per Pascal. So that all falls directly out of this. Okay, I realize I'm very close to using up all my allocated time. So let me just check in on the questions. Remy reminds us that at 10 kilohertz, 1 degree is equivalent to 0.1 millimeter in placement. And yes, thank you for that. I didn't have that calculation right off the top of my hand. That gives you an idea of the sort of mechanical precision. Now, of course, do you want your measurements to be accurate to 1 degree of phase at 10 kilohertz? That's up to you. A question, is the built-in VDD output possible to measure the current draw from that? So we do not measure inside the analyzer the current draw on the VDD. It would, I might have to think about that a little bit. You know, you could do the standard business of using a current sense resistor. The only problem is that, frankly, the current draw out of typical MEMS microphone is, you know, microamps, and you get into some challenges measuring that. So I might have to look into that, how to do that, but it's definitely not a built-in supply. Question, does APx500 support scripting, like writing a script to configure an iterative to save some data from the reference? And is it compatible with MATLAB and LabVIEW? So the quick answer to that is yes and yes. So we have a LabVIEW driver for APx500, and we also have some sample .m scripts for importing and exporting and controlling the analyzer from MATLAB. And then as far as scripting, unfortunately, it exceeds the scope of this demonstration, but we do have a built-in functionality in the sequencer for automating all the things being requested. You can either contact us directly or feel free to contact your local partner, and we can demonstrate that for you. And another question, person is using version 4.6 software. Apart from dual source, what are additional features are added in version 6? So the other features are the transfer function measurement itself, the sensitivity derived result, and we have a couple other small measurements we've also added. Can the digital and analog, you know, so that's a good question. Oh, the question is, can the digital and analog be measured together in a step frequency sweep? Let me double check that just right now in real time. And the answer is no. We only support it in the chirp-based measurements and transfer function and a few other measurements at this time, but we'll be adding support to that for the step sweep shortly. And Gerard asks, what are the 16 mics being measured in this array? Their frequency response magnitude looks remarkably flat, up to 20 kilohertz. I unfortunately can't look at them right now to physically tell you. I believe they're ST micro mics, but I can go verify what they physically are and email you if you want. Does the system cope with any changes of the reference speaker that occur between equalizations, or do you expect the reference speaker to remain stable? So the system does not automatically do anything. It is assumed that the reference speaker is stable. As anybody who works with speakers knows, that might be a bad assumption. So two things. I myself always equalize the speaker and calibrate the speaker when I'm starting a new test session. And second, that is the advantage of using a reference microphone in parallel, is that the reference microphone sort of is always correcting for the reference speaker, and measurement microphones are far, far more stable than speakers, many orders of magnitude. Next question is, do MEMS mics need calibration only once, or do they tend to drift significantly in sensitivity over time? So I'll begin my response by saying I'm not a manufacturer of MEMS mics, so this is really just my opinion. My experience with MEMS mics is that their sensitivity is very stable. I've had some MEMS mics that I've used for demonstration purposes for years, maybe as much as 7 or 8 years now, that still have exactly the same sensitivity as when I purchased them. This is a great question. The reference microphone that you are using is a pressure field microphone. If so, why not a free field one? Won't the measurements give you different results if you're using a free field, half-inch microphone, or a quarter-inch pressure field? So that's a very good observation. So let me explain a couple things. So the first thing is that at a quarter-inch, and this is another reason why I like quarter-inch measurement microphones, at a quarter-inch, a pressure field microphone and a free field microphone have the same frequency response in a free field. So if I'm making voice application measurements where my frequency range of interest is a few hundred hertz to 10 kilohertz, and I'm doing it free field, both microphones are work just fine. But the pressure field microphone's phase response is flatter. And this is, again, quarter versus quarter free field to pressure field. A pressure field microphone has a somewhat flatter phase response. I somewhat brushed by it, but just to bring that up. So the green trace on this slide is the phase response of a quarter-inch free field microphone, and it's just slightly off compared to the quarter-inch pressure field microphone. Another detail of a pressure field microphone that's not often exploited is if a pressure field microphone is at 90 degrees to the sound source, it has the same frequency response as a free field microphone. So that's something I've actually taken advantage of in this setup. That also gets the body of the quarter-inch microphone further away from the sound field at the microphone array. And then I think why are the frequency response measured with sweep and transfer functions so different? So actually, they're not different. We're getting a little bit of an illusion. Let me show you. This is just from 200 hertz to 20 kilohertz. In my transfer function result, I'm showing 20 hertz to 20 kilohertz. And what I have going on in my transfer function is a couple issues. So first of all, in the sweep, I'm starting up here. But the second thing is, again, going back to my coherence result, my test signal, the actual speech I'm playing back to calculate the transfer function, doesn't have significant energy above 10 kilohertz. So that's getting reflected in the results. My results with this particular test stimulus are not valid above 10 kilohertz because I don't have energy above 10 kilohertz, or in fact, very much energy below 100 hertz. Okay, another person asked, would like to do an amplitude step measurement and measure the noise in the presence of signal. How to realize that? So the first thing I'll say about that is there's a very, very practical challenge anytime we want to measure noise out of a microphone capsule, which is you're going to need a test environment that has less noise than that, and that might be a test box inside of a test chamber. It might be a concrete cylinder. It might be a vacuum cylinder. But you know, it's physically challenging because most of the time our environment is polluted with ambient noise. So for example, and this is something that you can do as a sort of sanity check, but if I go back to signal path setup and I just look at the sound pressure level that's ambient in my room without any signal present, it's 60, 70 dBSPL. So in that test environment, if I try and measure my microphone's noise, that's what I will measure. I won't actually measure the microphone noise. Then as far as the test itself, depending on what you mean by signal in the presence of noise, that might be just a THD plus N measurement. So I might just generate a signal, and one of the results is what's called the THD level or the THD plus N level. So this is the absolute signal level excluding the fundamental. And you could also do that as a stepped level sweep. That's a available result there. And then another question, could it be that minute acquisition doing simultaneous on digital and analog input lasts twice as long as just doing it on 2 analog inputs? So we notice, is there an explanation? I think, I'm not sure. That's an interesting question. Probably what we need to do is just get in touch directly with each other and better understand exactly what's going on there. That's not obvious to me. Oh, and then I think last question is, what about the distortion of the loudspeaker, especially when driven high? That's so it all depends on what you're measuring. And you'll notice that the measurements that I've demonstrated today are sensitivity, so the output of the transducer for a given sound pressure level input, frequency response, and phase response. Those measurements are not affected by the distortion of the loudspeaker. If you want to measure the distortion of the loudspeaker, if what you want to do is measure the distortion of your microphone, that is a challenge very similar to the challenge of measuring the microphone's noise. In this case, the problem isn't the environment polluting the measurement. In this case, the problem is that the vast majority of loudspeakers have far more distortion themselves than the microphones that we might want to measure. So the issue there is we can try and find a loudspeaker that has lower distortion than our microphone. Sorry, I got distracted. So essentially, we can try and find a speaker with a lower distortion than our microphone. That's quite challenging. In fact, it might be impossible. The more common thing to do is to not measure harmonic distortion. It's to measure intermodulation distortion and to stimulate the microphone with 2 speakers, each generating 1 of the component frequencies for an IMD measurement. Little tight on time here, but feel free to email us and we can walk you through that procedure. And then finally, a comment. I just measured a quarter-inch measurement microphone yesterday. Pressure mic at 90 shows -1 dB at 20 kilohertz, but about +6 dB at 80 kilohertz. And yes, that is entirely true. It depends on the pressure mic. Generally speaking, acoustically for sound applications, we're not too concerned about 80 kilohertz. It's also quite likely that the pressure mic is not flat. They do roll off at a certain rate, even, they don't tend to be flat all the way to their full bandwidth. Okay, so thank you for your patience. I realize we've gone over. If there are any additional questions, we'll try to address them, and also feel free to contact us via our support or sales channels if you do. Paige, do you have any closing remarks?
Yeah, thank you so much, Dan. Great work. And thank you everyone for attending. We will be having we will be publishing a blog post on this content, so be looking for that at ap.com. www.ap.com/blog. That will be posted in the next couple weeks. And also, I will be sending a follow-up email with a recording to this event, so you'll be able to rewatch if you need to. But thank you very much for your participation. And Dan, looks like we have one more question here in the chat if you want to address that.
Yep, I'll go ahead and address that. So the question is what about reflections from first to last microphone over the array? Wouldn't it disturb the frequency response for each array microphone at high frequencies? And yes, and that is absolutely correct. And if we take a look at our frequency response, and let's go. So you'll notice that our reference microphone has a pretty straightforward frequency response, but the frequency response, and this is highly, well, not super highly, but this is somewhat zoomed in, has all these irregularities. And each of the PDM microphones is not perfectly flat. They do take up some, they have some volume, and so that does tend to give us a, not a perfectly flat frequency or phase response. Unfortunately, it's sort of the translation from the idealized world to the physical acoustic world. Okay. Well, thank you very much, and I appreciate everyone taking some time out of their day. And
right. Yeah, thank you so much, everyone, and feel free to reach out to us if you have any questions or if there's anything else we can do to support you with your audio test needs. Take care, everybody.